Hello, I'm Bradley Alisam, and welcome to Community Statistics and Models number 2. Let me share my screen and get started. Okay, now we started with this first part, which was methods and time series, got to time series, and then section 2 is actually on networks. So we're actually going to look today, this time, at complex networks, and we're going to use the Rokwire community data as an example. We're also going to look at things called long tail signatures, and we're going to analyze a number of different communities data to get an appreciation for that. Let's start with complex networks. And I have not only do I have these data, but I have an open source version of the data here. And this is organized this is optimized for a platform called Gephi, G-E-P-H-I. And it's an open source platform for plotting and generating complex network data. So the way the data is structured is you have a series of nodes, and we have 21 nodes, which means we have 21 community members we're analyzing. And then we have edges. Edge file is much longer, and it's a pairwise comparison of all 21 contributors. So you can see that you have, for the first user, you have 21 targets. The second user, you have 21 targets, and so forth. And it goes down. And it's a lot of data, a lot more than the nodes file, but the nodes file is just used to specify a node, and then these are the connections. You can see there are a lot more connections potentially than nodes. Now, not all of these connections are active. Some of these are latent. So you can see that there's a weighted column here, and these weights are weights that have been created from the source data set. 0 meaning that there is no connection, although that we make that comparison of a pairwise relationship. And then these numbers up to 1 are the weight. So in other words, they have a stronger weight, the more affinity that 2 contributors have in that pairwise comparison, the larger this weight. And you have a weight of 1 if there's a maximal affinity. This is how this works. So this is basically a social network analysis. I call it complex networks because this is a field that's growing up quite a bit in your methods and techniques for analyzing the data, but it's really a social network analysis, and there are very limited differences there. So complex networks in general, and this could be social networks, it could be technical networks, it could be networks of anything you can think of, as long as it's appropriate to use this kind of model, allow us to examine the interactions between community members using select criteria. Each contributor is treated as a node that is connected to other nodes by edges. So these edges connect to contributors, which are weighted connections that represent specific community attributes. So I'll give an example, and then I'll kind of show what I mean. So an example is that you have a community of 10 contributors, and they're involved in 3 different activities: documentation, repository maintenance, and discussion leadership. Only a subset of contributors is involved in each activity. So that means that maybe you have 3 people doing, or 3 contributors doing documentation, 8 doing discussion leadership, and 5 doing repository maintenance, just as an example. So what that means is that only a subset of contributors is involved in each activity, but all 10 are involved in at least one of the 3. So this, affinity is distributed across all 10. So now what we want to do is we want to produce a graph that shows the relationships between all 10, and we want to show the connections, which are if you do the same type of activity. So this produces 3 subgraphs, which connect contributors in different ways. So you're going to have a subgraph of documentation people, a subgraph of maintainers, and a subgraph of discussion leaders. And they're all going to be connected. And you'll see that there's a spatial relationship there. There's a connectivity relationship that's actually quite useful for understanding what's going on in the community, and potentially different ways in which people can share and contribute. Network analysis can be an interesting way to discover subgroups in your community or find underutilized interpersonal relationships and affinities that bring people together. So if you want to learn more about this topic, I have some little bit of a bibliography here. There are several academic papers that can focus on open source communities and network analysis. So this is from the organizational and computation literature. So this is ACM computing surveys. This is Tamburi et al. 2013. This is organizational social structures for software engineering. So they're looking at software engineering teams and looking at social structure. Then this paper is also by Tamburi. This is also 2013, uncovering latent social communities in software development. This is in IEEE software. So you can see that they're looking at software development and these kind of latent or sub-communities. And so this isn't directly open source contributors, but it's basically in that direction. If you want to know something about what they call community structure, which is something that if you want to find these subgroups, and in the example I gave, it was very easy to find subgroups. But in a lot of cases where you have a lot of contributors, it's hard because it's not apparent to the naked eye where those divisions lie. It's hard to segment out a community or a subgraph. And so they have these, there's a field called community detection. It's a very active field. They use nice high-powered algorithms to discover these subgroups and define them. And so this is something in a field called community structure discovery or, community detection. And this is a paper that talks about this very specifically open source. This is also Tamburi et al. 2019, discovering community patterns in open source, a systematic approach in its evaluation. This is in empirical software engineering. This is another paper that you might want to check out. And then there's this George's data science article on social network analysis and applications in Python. This tells you how to implement a social network analysis. I am going to be using Gephi for these examples, but you can use Python. You can use some of the tools in Python to generate graphs as well. And you may need to reformat the data, but every piece of information you need is in the data set I just showed you. Now, I attended a workshop at last year's Networks conference, and this was called NetOpen. And it was actually run by the people, if you watched the first video, who did the archive paper that I featured on how to characterize contributors in your community. So this is really nice event. They had a lot of interesting talks. I gave a talk there on community networks, and I'm going to show you some slides from that talk. This is their website here. It's just a nice overview of some of these networks. This is a complex network in the background. They talked about some of these some different issues in the community. You're interested in looking at these large-scale fine-grained data sets for open science, citizen science, and open source ecosystems. So there's a lot of information here about different approaches to this problem. So I'm here. There was someone talking about assembling the collaboration puzzle. This is something we'll get into a little bit later. Crowd citizens in science. So they had a lot of nice topics here. Things about specific activities like bug triaging and how you analyze your development community to see who's doing that. And then you also have other talks like on different features in the network. So this is a nice, I don't know if they'll be doing it this year, 2022, but we'll see. So this is an example of what I'm doing here in Rokwire. So I told you that I had this measure in the open data set, and it was like the degree of affinity or the weight. And so the way I weighted contributors is by using this badge system. And so this badge system is ascribed to contributors every time they contribute something. And they do some activity, they earn a badge, or they get put in this classification. And so we have something where we have a list of these people with their badges, but you can take this data set and you can turn it into something interesting. more interesting than that. What you do here is you take your data for each badge and you look at the number of these badges that have been awarded. So you can see that like some of these badges have been awarded many times and some have been awarded very few times. And this statistical signature is called a power law or a long tail. And I'll talk about that in a little bit, why that's important. But just note that like you have certain activities like meeting attendee, where there are a lot of individuals in the community who are doing this, and activities like community building where you have a few people. And the idea is that each person has a number of these badges. And like the red one, you can imagine, is shared by a lot of contributors, whereas the orange one, and well, the yellow one as well, but the orange one is shared by very few contributors. So what I can do across individuals is I can count up how many badges they have, and I can make a comparison of which ones that they share. And so some of them share one, some of them share two, and some of them share more than two. And when they share more than two, then that means that their affinity is higher, and that weight gets closer to one. So we can see that there's a method for weighting the community connections between individuals and these pairwise relationships by these sorts of categories. So this is an example of a graph, and this was plotted in Gephi, as I told you. And this is an example. Now I'll zoom in a little bit on this so you can see what it looks like. So it looks like a mess. It looks like what sometimes they call these hairballs, because they're sort of these mangled structures, and you have to use different methods to get information out of them. So it's not immediately apparent sometimes what's going on. But so this is a full community network. So this is everyone in the data set who have at least one contributor badge in common. So that means that just about everyone is connected in some way. Now you notice immediately that there's some areas that are more highly densely connected than others. And you see kind of these triangles in here. And that's actually something you see a lot in networks, so these triangle motifs, where you have like not only like a pairwise comparison, but like three individuals who share like some set of attributes. And so this is part of the structure, internal structure of these things. They call these three-way or four-way motifs or patterns. Oftentimes they'll call them like motifs, or they'll call them like cliques, because there's high everything's fully connected locally. And so this is interesting because that could mean that those contributors work on projects together, or that could mean that they don't work on projects together, and they should be working on projects together. This is where the value comes in. So you can see that there's some structure here, and we would need to use network statistics to tell us exactly what the sort of the structure is of this. You can use things like network diameter, you can things like centrality, there are different measures you can use, but those are kind of crude tools. So another thing we can do, and we can also use the community detection algorithms, although this network is pretty small, so it might not really do very much for us. Another thing we can do, though, is to use those weights and use the identities of the nodes to drop things out. So we can use the weights. In this case, we're interested in the community manager who's here. That's me, and I know who that is. And I, being involved in everything, I have all the badges. So that's kind of interesting. But that means that I'm connected to everyone. And but I'm also connected very strongly to people who have done at least three things, or at least have at least three contributor badges. So you can see that there's this motif, this fan, what they call fan motif. So there's like a fan comes out from a single source, and I'm the head of this fan motif, and you can see what that looks like. And so that shows you what happens when you use these two criterion to build a graph. And it comes from this graph. This next one is where I take the community manager out of the equation and I just look at the connections. So this network looks a little bit different than this network. It looks a little bit less dense, and there's a core here where you have high rates of connectivity between individuals, and then others that are up here. This is also an artifact of the way that the nodes are placed in the space. These don't map to any sort of spatial variable, but they're often put in ways that show the maximal structure. So the algorithm, the visualization algorithm does this, but You see again these sort of these cliques inside here, but you also see that if I do the same thing, right now I use individuals who have contributors who have at least 2 contributor badges in common, and I take out the community manager. We don't have this fan motif anymore. We have this sort of fan motif, but also this area here, which is, I don't really know what to call that, but it's a lot different than what we have here. And I changed the criterion slightly here. I've done at least 2 badges, but it does show this sort of relationship. So you can see different patterns and relationships. Sometimes you can characterize it with summary statistics. Sometimes it just tells you, if you know the identity of the nodes, who in the network is connected to whom. And then, maybe those people are working together on something, maybe not. But that's something you can evaluate later. So the next thing I'm going to talk about is advanced interpretation. And so going from networks to advanced interpretation, we have something called, I just talked about with respect to the Rokwire community data, a long tail. So what is a long tail? If you go to Wikipedia and you look up long tail, it's paraphrased as a distribution with a central tendency or the region of support. And so in a bell curve, it's in the center and it's that hump is distinct from the tail. Okay, so in a normal distribution, for example, the central tendency is distinct from the tail. The tails are considered to be outliers. They, they kind of go out for a long time, and they're considered extraneous variants. So a lot of people just cut them out when they analyze their data, and that's not necessarily a good practice, but some people do this. And then, it's basically people want to know what the central tendency is. So, but the thing about long tails is that with a long tail distribution or exponential distribution, we have this area of support, but then we have this tail that goes out for a very long time. And that tail is important because that's where most of the values are, as it turns out. So if we take like a data set and we rank order it by, say, like number of contributors or number of contributions per contributor, and we have like 500 contributors, and we rank order them by their number of contributions, you're going to have some, a relatively small number of people with a large number of contributions, and then a lot of contributors with relatively few contributions. So that's going to form this long tail, and it's going to go on for a long time. And there's information in it. The information being is that that's most of your contributors. So that's important information to have. So the long tail is something we're really interested in here. So this has to do with frequencies of occurrence or counts or rank order analysis, but it also has these data that you don't see. It's like time series. It's a different type of data from the normal distribution and from things like t-tests and other types of parametric tests. So this is an example from the Wikipedia community. And so Wikipedia has a really nice data set of contributor data. And if you go to this site here, this is actually a Wikipedia stub where they have a list of Wikipedians by number of edits. And if you plot this out, you find, first of all, there are different categories of contributors. So they're different, I don't know how many categories there. I think this is like the top 20 or maybe more, or top 16, something like that. And I plotted them out to show that there are many contributors in certain categories and very few contributors in other categories. And this forms a long tail. Similarly, if you look at the number of contributors and you look at their edit count, so this is edits per user categories, this is the count of edits. So this is this count versus the categories that exist, and you see this pattern. You also see it for the number of contributors making edits. So these are kind of related graphs, but there are different types of data that I'm using just to show this tendency. So the more edits you have, the fewer contributors are doing more edits. Different categories have fewer people in them. And what does that mean? So what it means is that this is this small graph up at the top, but it's blown up now. And you can see that there are different categories here. And what we find is that when we look at the annotations of the categories, we can see that the top 5 rows here, 1, 2, 3, 4, 5, these 5 here, involve verification and administrative permissions. So that means that what happens in the Wikipedia community, so people come into the community and they start doing these 5 different categories, or they engage in these 5 different categories first. It allows them to build trust through demonstration and utilizing skills built through demonstration. So, you don't want people to go in right away and start editing pages without, they have to gain certain permissions. And so they're not really making decisions about it. They're sort of doing these perfunctory editing functions. And then there are other contributors in these categories, very few relative to the whole number of contributors in the community, who are doing things like overseeing the edits, making decisions about what should be in a page and so forth. So we talked about this with respect to discourse, the platform discourse, and they have these trust levels. And trust levels are actually interesting because Wikipedia uses a similar technique here to sort of bring people into their community and sustain people. Now, that being said, I imagine that this large number of contributors, there's a lot of turnover, people come and go. But in this group here, in the smaller group of individuals in these different categories, there's probably much less turnover. So the stickiness, as they said in the discourse example, is, it's reserved for a small number of people, but those are the people you want for these other categories. So that's the Wikipedia experience. Now, in general, long tails, and I think I talked about this a little bit, but I want to reinforce this. Long tails are properties of an exponential distribution. So that's what they call it. It's not a normal distribution, it's an exponential one. Nice heuristic is the 80-20 rule. This was something that was developed in the 19th century by Pareto. And if you've heard of Pareto equilibria, you know that this is basically a similar concept. And the 80-20 rule was developed by looking at income inequality data in Italy. And they found that 80% of the wealth was held by 20% of the people, and 20% of the wealth was held by 80% of the people. So they had this kind of distribution that was not, not equal. So it was unequal, but it was very specific, and you can replicate this across different systems. Actually, it's interesting. You can replicate it across like city sizes and other types of things. So it actually works for communities, but it's a very deep principle. So I talked about this in statistical terms. This 80-20 rule states 80% of the density in Y, which is this Y axis, this density, meaning the number of things in the data set, is represented by 20% of X. So this is like 20% of X. This is 80% of Y, all of these things added up. Well, 20% of the density in Y, which is this area here, is represented by 80% of X. So this area here. And you'll see that this is, this happens again and again in these graphs. There's a reason, because it's the principle. Okay, so we can use this same principle, however, to characterize the potential for hierarchical relationships and contribution disparities in our communities. So we can look at this, and remember I talked about income inequality earlier. We can look at this to understand who's contributing and who's not. Or if there's some disparity, and we want to correct the disparity or account for it, then we can use these to understand what, a little bit more about what that is. This also tells us about hierarchical relationships. So in the Wikipedia community, these people are sort of above these other people in terms of the hierarchical organization. These people are sort of admins for these people, all right? And you're going to have this in communities that are big enough, because there needs to be this kind of administrative structure. And so you end up with this hierarchy, and this is kind of the signature of a hierarchy. So the long tail property can tell us how much of our community is there to participate in a passive manner, or as a potential source of contribution not yet realized. So we can tell a lot of, well, we can't really tell for certain, but we can detect these things and then go back to the, maybe some qualitative data, or go back and survey our community to confirm what we see in the statistical signature here. Okay, So, and then this actually relates to networks because these type of long tails actually have like a network signature. And that is you have a lot of structure, say in the center of a network, and then less structure at the outskirts of the network. So you have things like small world or scale-free networks, where you have what they call hubs, which are nodes that are highly connected compared to the other nodes in the network. That's something that's a hierarchical signature. And you can tell through these kind of distributions. These kind of distributions yield that structure in the network. So now I'm going to talk about the OpenWorm community. And in the OpenWorm community, I did an analysis on data from 2016 through 2020, and this was on the Slack team. So this was data that was gotten from the Slack team. This is de-identified data except for categories which I've defined in the legend here. And it shows you the number of log number of Slack messages. So people are sending a lot of Slack messages versus very few Slack messages. And we have 228 contributors in this analysis. So you can see that we've ranked the contributors by their number of Slack messages sent. And we can see in this graph, and the color is a little bit hard to make out in some parts, but basically this blue category is senior contributors. Red is Google Summer of Code students, people who are involved in that internship program. Board affiliates are people who are involved in the board of directors. Major collaborators are people in green. Those are people, I think I talked in another video about people offline contributors. These are people, stakeholders from the scientific community, and then other in gray, which is people who just come on and they're just, casual contributors where they don't have a role. Now we see something interesting. We see this long tail, but we see that if we ascribe specialized roles in the community, that all of those roles tend to be people who send a lot of Slack messages, or they tend to have some invested interest in the community. None of those people are sending very few Slack messages, which means that they're very busy in the community, which is expected. You also see, though, that there are gray dots up in this area of the distribution, up in this 20% of X. And so what's going on there is that these are people without, maybe they are leading a project and they're not a senior contributor, or maybe they're doing a lot of work on some specific thing. I know from experience in the community that we had a robotics team where there were people working, weren't senior contributors, and were working very hard on like a 3D printed robot or something. And it was just something that took a massive number of Slack messages. And then, that's reflected in these data. So you get a lot of people like that. Now, the reason I point this out is because, you can create categories for people, and that tends to encourage them to contribute and participate. So senior contributors might be people who are leaders of projects, or they've been around a long time. Typically, if they've been around a long time, they're working on things. So this is all very good. And I don't know, this might be something that is changed because some senior contributors might fall dormant, or some Google Summer Code students might fall dormant. But this is over a long enough period of time so that it kind of washes that effect out. So, I think it's interesting to see how, ascribing roles to people in the community can increase their participation, at least in the Slack, and how, it doesn't necessarily preclude people who don't have these specialized roles to come in and do things and actually spend a lot of time contributing. So this is about mathematical models and division of labor. So one theme that arises from both the Rokwire community and OpenWorm data is the classification of contributors into skill and experience grades. How do we characterize the potential stable forms of collaboration in a community? One way is through the application of agent-based models. So I've been doing some work in one of my other groups on applying agent-based models to open source community development and open source software development. And this uses a platform called NetLogo. And NetLogo is an interesting package because it's a very well developed package. It's really only very well developed agent-based modeling package. But it builds these agent-based models. And agent-based models are these like spatial arrays of grid cells. And you populate each grid cell with an agent, computational agent. And those computational agents interact with one another. So it's kind of like a network, except it's a generative model, and it produces data. If you give it certain conditions and you give it certain sets of interaction rules, it can generate a lot of data for you. And it can actually characterize your community in ways that your data may not tell you. So this is an interesting approach. There are libraries in NetLogo that we can use to kind of, maybe define some of these rules a bit more. So there are all sorts of like social science models, and there are game theoretic models like the prisoner's dilemma that might be mapped to what's going on in a community. And then you can tune the parameters, the payoffs, the interaction rules to reflect maybe something going on in your community or in some hypothetical comparison where you say, I want to see what happens when a lot of individuals cooperate versus one where they kind of stay on their own or they defect, in the language of the prisoner's dilemma. So you can actually measure that, and you can look at the outputs over time, and you can actually then use that as data. And so this is a way to generate data that you can't necessarily collect from your other measures. Another approach is to use information theory. And the reason we want to use information theory is to understand sort of the reconfigurability of expertise. And so I use that term to refer to a situation where there's constant churn in your community. People are doing different things, people are coming and going. And if you can take advantage of that reconfigurability, you can do a lot of nice long-term projects. I've done this a number of times with software development and with other types of academic work where you have a goal, long-term goal, and you bring people come in and with different skills and you leverage those skills. And then over time, you've built a very large collaboration of people and you've gotten an end product. So this is something that we want to understand, but the way to do that statistically is through information theory. So this is something that we can calculate the information content of these badges, these ascribed labels to people in the community. And we can also use subgroups that we identify from our networks. So we can use the measure of information content known as Shannon information, or H. And so H is measured by this, this defines an ensemble of states. So the states occur with a certain probability, and then you sum them up and you have this H value. And it gives you an information measure. Basically, the more variation you have between your individuals and your ensemble, like their state is different, then if they're present or absent or their state is different, there's more variation in that, the higher your H value. If you have maybe a community or you have a group where you have maybe, let's take expertise as an example. Everyone in a group of 10, say, has the same experience. Well, the H value would be almost 0 because everyone has the same expertise and there's nothing to be gained from that in terms of reconfiguration. But if everyone in that group of 10 have different skills, then the H value is extremely high. And so then we can say that there's something really to be gained from reconfigurability of expertise. And we also can maybe look at the inputs of the community, the onboarding process, who's coming in, who's leaving. So you can characterize all that using information theory. So from the Rokwire community example, if every member of a subgroup is of the same category, the value for each is small, while a broader representation of categories results in a large value for each. So this is the badge data. This isn't going to be something we're going to look at right away, but this is just an example of the badges and individual contributors. And suffice it to say that, you have a lot of individuals with one badge, fewer people with 2 badges, and then there's a small group of people with more than 4, and then the community manager with like 8. So this is an example here of individual contributors and the number of the different types of badges they've earned. You can see a lot of red badges, some green and yellow badges, some black badges. And so That's basically how, and then you can calculate the information content of this group of contributors in this table, or a subset of these people. And you can say this subgroup has an information content of that's high or low, and then that tells you something about, that group's potential for reconfiguration. So they might be able to, you might be able to disperse that expertise to other groups, or you might have new people join in and augment the group or enrich the group in some way. Okay, so that's one way you can use information theory on categories of contributors. Another way to do this is to look at the geographic distribution of people by time zone. And time zone, I think, is an underappreciated factor in community building, because especially if you have like a large virtual distributed group, and I've dealt with these groups before, you have people all over the world. You have people in East Asia, you have people in South Asia, you have people in Europe, people in the Americas, and they're all in different time zones. And this is actually quite hard. Trying to schedule a meeting, for example, between Australia and North America, it's extremely hard because there's like a 14 or 15-hour time difference. And so that can be very bad. You don't necessarily want to schedule a meeting directly, a regular meeting directly. So you have to account for this. And of course, you can use information theory to calculate in one of these subgroups, how many different time zones are represented, or what's the time difference representation in there. So you can look at those sorts of things and get a number. And that will tell you, your smaller H value will be desirable because everyone will basically be in the same time zone. A larger H value is less desirable because people are scattered all over the world. What will happen in a lot of communities that have these time zone differences, huge time zone differences, is that they'll have like 2 meetings on the same issue. They'll have meeting 1 and meeting 2. Meeting 1 being for people in maybe from like South Asia or Australia to East Asia, and maybe one in the Middle East, and then a second one, Europe, North America. And then, it doesn't suit everyone perfectly, but at least they don't have to get up in the middle of the night work. So this is useful for people. And you also have to consider that people have different internal clocks. So sometimes people don't want to do this in the morning, they want to do it in the evening. And again, if you are scheduling a meeting in North America for the evening, that excludes people in other parts of the world. Some people like to work in the middle of the night, I don't know. But, these are all these things you have to weigh. And I think this is a standout topic, because this is something that transcends data analysis or even any sort of model. This is something to be aware of and mindful of. But you can also analyze this data. You can use a survey to ask people, what time zone are you in? Or you can even get this from the Slack channel. Usually each person has a time associated with their profile. But in any case, you have the data, you can analyze it and find the optimal settings for your community and the subgroups in your community. So this is an example of reconfigurability of disciplinary expertise here. You have this network of individuals with different skills and different colors. They're distributed around the world. So there's another network of geographic network. So you have 2 networks that you have to integrate. So this is actually quite useful in terms of understanding multiple aspects of your community. And then this is an example of reconfigurability of disciplinarity or expertise. You have 2 different skills here, and you're drawing circles around your subgroups that you want to be engaged in some sort of activity, and you want to make sure they're well mixed groups, because if they're not, then you can't really do what you want to do. So you want to manage expertise in different ways. And depending on the task or depending on what you're doing, you may want more of one expertise than another. And so information theory can help, network theory can help, and even this long tail methodology can help with this as well. So thank you for watching this video. That concludes our module, and that concludes our series for this course. I hope you enjoyed it. I hope you find it useful.